Hello everyone and welcome to lecture 16. Today we're going to talk about how to represent instructions in hardware. So last time we began part 2 of the course, which is the instruction set architecture, the interface between hardware and software. And we said that an instruction set is the set of instructions recognized by a computer, and the different processors have different instruction sets. And the instruction set that we're going to focus on in this course is MIPS. However, the concepts that we are covering can be extended to any of the other modern instruction sets. We started by looking at arithmetic instructions. For example, add A, B, C is an instruction that adds B and C and saves the result in A. So it does A equals B plus C. And we said that the operands for instructions are actually registers. So the processor has a register file. In the MIPS processor we're looking at, our register file has 32 registers that are 32 bits each. And the operands to our instructions are going to be these 32 registers. And because a register is 32 bits or 4 bytes, this quantity of data has a special name, which is a word. So a word refers to 4 bytes or 32 bits or the data that can be stored in a single register. We also saw that registers have names. They have human readable names that allow us to remember what each register is intended to be used for. And we started working with the T registers and the S registers, so registers T0 to T9 and S0 to S7. And we said that there are other registers that we will look at later. But for now, the T registers are registers for temporary values, and the S registers are registers we use for saved values. These are things like local variables where we want to keep the value around for a long duration of time. Whereas the T registers are temporary values that we use only kind of to store intermediate expression values. We then looked at an example of how we can take kind of high-level code written in something like C and convert it to low-level MIPS code. We saw how we have this expression here, f equals g plus h minus I plus j. We took this and we broke it down into individual instructions where every instruction did one operation with 2 inputs and 1 output. So here we broke this whole expression into g plus h, which was the first instruction, I plus j was the second instruction, and then the 2 results subtracted from each other was the third instruction. We then introduced memory instructions. We said that, obviously 32 registers is not enough to store all the data that we have in a program. So we put frequently accessed data in registers, and the rest of the data is in memory. So we need a way to load and store values from memory, and that's why we have load and store instructions to do that. We said that memory is organized as byte address. So every byte or 8 bits has its own memory address. So here address 0 points to 1 byte, address 1 points to 1 byte, address 2 points to 1 byte. But we also said that words, because we said that we were interested in looking at data at the granularity of words, we said that words are aligned in memory. So a word in memory, which is 4 bytes, has to exist at an address that is a multiple of 4 bytes. So here at address 0, I have a word consisting of bytes 0, 1, 2, and 3. At address 4, I have a word consisting of bytes 4, 5, 6, and 7. At address 12, I have a word consisting of bytes 12, 13, 14, 15. But for example, I don't have a word at address 13 consisting of bytes 13, 14, 15, and 16. The reason is that 13 is not a multiple of 4. So all accesses to words have to be multiples of 4. Okay. And we also looked at the notion of big endian and little endian. We said that when we come and we want to store a 32-bit word or a 4-byte word in memory, how to distribute these values, these 4 bytes across the 4 bytes comprising the word depends on whether the machine is big endian or little endian. So in a big endian machine, the most significant byte goes into the least address in the word, whereas in a little endian machine, the least significant byte will go into the least address of the word. Okay. Then we looked at memory instructions, and we saw how if I have something like a of 12 equals h plus a of 8, here a of 8 and a of 12 are memory locations, they're not registers. even though I have the pointer to A, to the array A in a register. So the way we dealt with code like this is by issuing load instructions for memory accesses that are reads, like and store instructions for memory accesses that are writes. Okay. And these load and store instructions, in the instruction, they have this base register and an offset, where the base register is the beginning of the array, and then the offset, here 32, corresponds to 8th element times the size of a single element in bytes. So here array A is an array of integers, so every element is 4 bytes. So 8 elements times 4 bytes per element, that's 32, and that's where 32 came from. Okay?
Professor,
Yes.
if we need the A of 0, we only call as 3.
No, you would put 0 as 3. So here, rather than 32, you would just put 0.
Okay.
Okay. Okay, so this was a brief overview of what we covered last time. Any other questions about what we covered last time? So someone's asking, since each row represents 1 byte, then each square contains 2 bits? No. So I said that over here, every row was 1 byte. Okay, so over here, address 0 points to 1 byte, address 1 points to 1 byte, address 2 points to 1 byte. Okay, but in this diagram over here, what we said is that every word consists of 4 bytes. Okay, so here the word at address 0 consists of the byte at address 0 and the byte at address 1 and the byte at address 2 and the byte at address 3. Okay, so here this row does not only refer to the byte at address 0, it refers to the word at address 0, which is 4 bytes. That's why we have 4 squares over here. So each square is 1 byte, the square is not 2 bits. Okay, other questions? Okay, well, if there are no questions, there are a few more instructions that we did not have time to cover last time. So what I'm going to do is I'm going to cover the remaining instructions, and then we will move on to talking about today's topic, which is instruction representation, or how to represent instructions in hardware. Okay, so the next type of instructions I'd like to talk about is immediate instructions, which have immediate operands. So what is an immediate instruction? Or what is an immediate operand? An immediate operand is an operand to an instruction, which would be called an immediate instruction. And this operand has a constant value. So for example, sometimes we want to add 2 variables, right? So before we saw how we added G plus H and each of them was in a register. But sometimes we want to add a variable to a constant, okay? So maybe I want to do X equals X plus 1 or X equals X plus 4, okay? So if I want to add a constant, there are special instructions called immediate instructions, or that have immediate operands. And these instructions take not just registers as operands, but also constants. So here, add I means add immediate. And what add I does is that it takes, what it's doing here is it's doing S3 is equal to S3 plus 4. So the two sources, rather than having 2 source registers, it has one source register, and then the other operand is a constant value. And then the destination register is, in this case, S3, which is the same as the source register. So here we're doing S3 equals S3 plus 4. The reason they call it immediate is you can think of it as rather than, if we want to add a constant, rather than having to somehow, maybe this constant exists somewhere in memory and then we want to load it from memory and then add it, we just get the constant immediately via the instruction. Okay, so that's one kind of a rationale why they're called immediates. Okay, so here add immediate will add a constant value to a register value. So the immediate operands, again, they avoid having to load constant values. So if I have a constant value in my code, rather than having to kind of store it ahead of time somewhere in memory and load it when I need it, I can just get it immediately via the instruction. Now, one catch of immediate instructions is that they're limited to small constants. I'm going to explain why later in today's lecture, but for now, it's good to understand, good to know that these immediate instructions are limited to small constants. So I cannot add any 32-bit integer here. I cannot pass any 32-bit integer as an immediate instruction, as an immediate operand to an instruction. They're limited to small constants. And this follows a design principle that we have when we build computer architecture, which is to make the common case fast. Okay, what do I mean by make the common case fast? Well, most of the time when we add constants, we don't really care about adding very large constants. Most of the time when we add constants or when we subtract constants, they're usually small values. Okay, they're usually small values that we add. So it's good to have an instruction that makes being able to add a small constant using one instruction is important because we commonly add small constants. Now for large constants, we're going to have to use multiple instructions, and we'll see that later. But that's okay because it's not very common for us to add large constants. So it's unnecessary to create an instruction that helps us add large constants. Okay, so we make the common case fast by providing an instruction for small constants, and large constants, which are less common, we need more instructions for those. Okay. Finally, there's no subtract immediate instruction, and the reason is that this constant over here is going to be a signed value that we'll represent with 2's complement. But for now, you don't worry about how we represent it. What's important is that this constant here can be a negative number. So we don't need subtract immediate, we just do add immediate and provide a negative constant. Okay? Any questions about the add immediate instruction? Is it clear? Okay, well, the next thing I would like to talk about is the constant 0. So if a lot of times, wait 1 second. So someone's asking, what do we do with big constants? I will talk about that in a future lecture. So please hold that question, and in a future lecture, we'll see what we do with larger constants. So here, the constant 0. So 0 is a very important number. We use it in a lot of places. And because of that, MIPS actually has a register, which is register 0. And that name of that register is 0. Okay. And the special thing about this register is that this register always stores the constant 0. So this register, we cannot write to it. Okay, if we write to it, it doesn't change the value of the register. The value of this register is always 0, and it cannot be overridden. Okay, now why is it useful to have a register whose value is always 0? Well, it's useful in many different situations. One common use of the register 0 is, let's say we wanted to move a value from one register to another register. Let's say we wanted to move a value from one register to another register. Well, one way we could do that is by providing a move instruction. Okay, one way we could do that is by saying, okay, we have a move instruction. It takes 2 registers, and it moves the value from one register to another register. But actually, we can, rather than having an extra instruction, we can use one of the existing instructions we already have, which is add, and use the 0 register and basically add 0. So if I do S1 plus 0 and store the result in T2, what I've basically done is I've copied S1 into T2, because adding 0 doesn't change the value of S1. Okay, so this is one common use of the register 0. I'm showing you this as an example. There are other examples later we'll see where we will use this register 0. But for now, it's just good to know that a register 0 in MIPS is named 0, and its value is always 0, and it cannot be changed. And we use it in many different places. Okay? All right, the next topic I would like to talk about is logic operations. So we've seen arithmetic operations, we've seen load and store operations, and the arithmetic operations we've seen there are versions that add 2 numbers, 2 registers, and there are versions that add a register and an immediate value or a constant value. Now we're going to look at logic operations, and logic operations are used for bitwise manipulation. So here, a single AND in C or a single AND in Java refers to performing a bitwise AND. So one caution here, this is different from the 2 ANDs, right? When you have 2 ampersands like this, that is a Boolean operation. It takes two Booleans, gives you a Boolean. But here what I'm referring to is the single ampersand. The single ampersand is a bitwise AND. So it takes two integers. It does an AND operation for all the bits, like we saw in the lecture on building an ALU, and gives us an integer where each bit of that integer is the AND of the two corresponding bits in the operands. So we have an AND and an AND immediate instruction. For bitwise OR, which is a single OR like this, there's OR and there's OR immediate. So as you can guess, AND takes two registers, whereas AND immediate takes a register and a constant. OR takes two registers, does the bitwise OR, whereas OR immediate takes a register and a constant, and it does the bitwise OR. There's a bitwise NOT, okay, which is this tilde over here. So if you want to take a value and you want to invert all the bits in that value, you use the tilde operation in C and in Java. Again, this is different from the exclamation mark. The exclamation mark does a Boolean NOT. Okay, so the exclamation mark will take a true value, make it false, take a false value, make it true. This is different here. This tilde actually inverts all the bits inside of an integer. So here you'll notice that we don't have a NOT instruction, we actually have a NOR instruction. And I will talk later about how we implement NOT using NOR. We have shift left, which takes a value, takes an integer and shifts the bit of that integer left by whatever value we give it. And we have shift right. Okay, so shift right also it takes an integer and shifts the bits in the integer to the right based on whatever value we give it. Okay. So let's start by talking about each of these operations. So what does a bitwise AND do? For example, if we had AND T0, T1, T2, what this means is that T0 equals T1 and T2. What does it mean to do a bitwise AND of T1 and T2? Well, let's say T1 looked something like this. Let's say T1 looked something like this. Okay, it had a bunch of zeros, but it has a bunch of ones over here. And let's say I was interested in a specific window of bits in T2. So let's say I was only interested in these bits over here. I wanted to look at what these bits are, and I wanted to ignore all the other bits. So in this case, I might want to do something like apply a mask. Okay, what do I mean by apply a mask? I want to clear all the other bits in this 32-bit value, and I only want to keep these bits whatever their value is. So one way I could do this is by doing a bitwise AND of T2 with a mask T1. So here T1 will have ones for all the bits I am interested in and zeros for all the other bits. So now when I do a bitwise AND, what's going to happen is for all the bits where T0 is 0, those are going to get cleared. And for the cases where for all the cases where the bits of T1 are 0, the bits in T2 will get cleared. And for all the cases where the bits in T1 are 1, the bits in T2 will remain. So I'm going to get something like this. Okay, so here by doing a bitwise AND, this is just one application of a bitwise AND. By doing a bitwise AND, what we can do is we can do bitwise operations on integers where I can take an integer or a kind of a 32-bit value and then extract a window of bits and clear all the other bits. Okay, so this is how a bitwise AND works, and this is just one of the applications is to mask the bits in a word. Okay. Another logic operation is a bitwise OR. So a bitwise OR takes T1, T2, does a bitwise OR, and stores the result in T0. And the way the bitwise OR works is as follows. The bitwise OR is useful if I want to set a specific bit inside of a word. So for example, let's say that I have this value over here in T2. These are 32 bits. And let's say I want to set a specific set of bits. Let's say I wanted to take these 4 bits over here and I wanted to set them all to 1. Okay, and I didn't want to do anything with the other bits. The other bits, I just want to keep them the way they are, but I want to set specific bits inside of the word. Well, the way I could do that is by doing an OR operation, a bitwise OR operation. How does that work? Well, for the bits I want to set, I'm going to pass a mask, and that mask is going to contain ones for all the bits I want to set and zeros for all the other bits. And when I do a bitwise OR operation, what's going to happen is anything OR 0 is going to be 0. So everything outside this window is going to remain as it is. but then anything or 1 is going to be 1. So everything, all the bits inside this window are going to be set to 1. So that gives us a result like this. So here all the bits in T2 that are in the window are set to 1, and all the other bits remain as they were. Okay, so this is how a bitwise OR operation works, and this is just one application of bitwise OR, which is to set specific bits to 1. Okay, any questions about logical operations, bitwise AND and bitwise OR? Are these clear? Okay, well, finally, the NOT operation. So a NOT operation is useful for inverting the bits in a word. So let's say I have a word, I want to invert all the bits in that word. So if they're zeros, I want to make them ones. If they're ones, I'm going to make them zeros. Well, the way it works is if I have T1 like this, which has a bunch of zeros and a few ones, if I apply a bitwise NOT on it, I will get the value like this. So all the bits that were ones become 0, and then all the bits that were 0 will become 1. Okay, this is how a bitwise NOT operation works. Well, it turns out that there actually isn't an instruction in MIPS that does a NOT operation. There's actually something better. We have an instruction in MIPS that does a NOR operation, and a NOR operation has 3 operands. It has 2 inputs and 1 output. Okay, so if you remember when we built an ALU, we actually did not we did not have a NOT operation in the ALU. We had an AND, we had an OR, we had a NOR, right? We had an AND too, but we're not going to use it here. Okay, but we didn't have a NOT operation. The reason is that NOR we can use NOR to implement NOT. Okay, you can use NOR to implement NOT, so it's not necessary to have an extra instruction NOT, right? That's just an instruction that we don't want to have any instructions where we can do the same thing with 2 different instructions. That's redundant in our instruction set. It makes our hardware more complex. We want to have as few instructions as possible. So if we can do NOT using NOR, we'd rather just have a NOR instruction and not have a NOT. Okay, so yes, as you guys are observing, we can implement the way to implement NOT using NOR is as follows. We know that A nor B means not A or B. Okay, so if I want to compute not A, I can simply use NOR and pass A as one of the operands. And what do I pass as the second operand? Well, one way to do it is to do A or A, fine, right? A or A is just going to be A. Another way to do it is to do A or, right? A or what always gives me A? 0, exactly, 0. So one way to do it is A or A. Another way to do it is to do A or 0. So if I want to do a NOT operation, I want to do T0 equals not T1. The way I can do it is I can do NOR T0, T1, 0. What this means is that T0 equals T1 NOR T0. In other words, T0 equals not T1 or 0. Well, T1 or 0 is just T1, so not T1 or 0 is basically not T1. Okay? Any questions? Okay, well, with that, we are done. Again, register 0 is always 0. This was another use of register 0. We're not done. We have one more set of instructions, which are the shift instructions. There's a shift left logical, which takes a value and shifts all the bits to the left. And when we shift bits to the left, what's gonna happen is that we're gonna have bits on the right that are left empty. And what we will do is for these bits is that we'll fill them with zeros. So shifting to the left is actually equivalent to the instruction for that is SLL, and shifting to the left is actually equivalent to multiplying by 2 to the power I. So if I shift a value to the left by I bits, this is equivalent to multiplying by 2 to the power I. I hope that's clear to everyone why that is the case. Shift right logical, if we shift a value right, what we'll do is we'll fill the bits to the left, and we're going to have empty bits appearing on the left, so we can fill those with zeros. Not always, by the way. We can also fill them with ones if we have kind of a negative value. So how shift right behaves is different based on signed or unsigned integers. And SRL, which is the instruction for shift right logical, if we shift right logical by I bits, this is equivalent to dividing by 2 to the power I. And this only actually is equivalent for unsigned values, not for signed values. Okay, so shift left, shift bits to the left, which is like multiplying by 2 to the power I, and shift right, shifts bits to the right, which is like multiplying, dividing by 2 to the power I. And shifting, by the way, is it's much cheaper than multiplying and dividing. So a lot of times if the compiler detects that you're multiplying or dividing by a power of 2, rather than generating a multiplier or a divide instruction, it'll actually generate a shift left or a shift right instruction. Okay, so now we are done with talking about instructions, and the next topic I'm going to move on to is how to represent instructions in binary. Okay, before that, any questions about instructions in general before I talk about representing instructions? Okay, well then let's move on to talk about representing instructions. So instructions are data, right? Instructions are data, just like integers are data, ones and zeros, just like strings of characters, A's, B, C, and D are data. Instructions themselves are data. What do I mean by that? So when a processor executes a program, right, it executes instructions. Where does it get these instructions from? Well, it gets them from memory, right? The processor is going to load instructions from memory, and it will execute these instructions. Okay, so when you write a program, you compile it, they get stored in a file, the instructions get stored in a file. Okay, and then the processor is going to read that data and is going to execute those instructions. So what we need a way to store instructions in memory, right? We need a way to represent instructions as binary values so we can store them in memory. And that's what we're going to talk about today. So we need a way to encode instructions in binary. And binary encode instructions, by the way, are called machine code. So when you hear machine code, what this means is the instructions that we've talked about so far, but encoded as binary values, encoded as zeros and ones. Okay, so how do we do this? How do we represent instructions as binary? So in MIPS, every instruction is encoded as a 32-bit word. Okay, so every instruction in MIPS is 32 bits. Okay, and MIPS has a very small number of formats. Actually, has 3 formats. What I mean by format, a format is like a template for storing an instruction as a 32-bit word. It's a way to represent instruction as a 32-bit word. And MIPS has a small number of formats. And these design principles, where every instruction has a fixed number, has a fixed size, and there's a small number of formats, this favors regularity. So again, I told you before that the MIPS advocates for simple and regular instruction sets. And not all instruction sets are like this, by the way. So there are some architectures that have variable length instruction sets. So there are architectures where not all instructions are 32 bits. Some instructions might be 16 bits. Some instructions might be 64 bits. Every instruction has a different size. Okay. And there are architectures that have many more formats than just 3, which is what MIPS has. Okay, obviously, if instructions are all different sizes, they will need to have different formats. Okay, now this has pros and cons. The advantage of having instructions with variable length instructions, having architectures with variable length instructions, is space efficiency and flexibility. What do I mean by that? Well, if an instruction has variable length, it means if an instruction is very simple, I can store it in 16 bits. Okay, so I can save space. Okay, so this is an advantage of having variable length instruction. Okay, whereas in MIPS, every instruction is 32-bit word. So if I don't need all the 32 bits to represent this instruction, the instruction is still going to occupy 32 bits, even though some of those bits may not be needed. So this is a waste of space. Okay, however, it simplifies things because I know that every instruction is 32 bits, whereas here, when every instruction has different size, I need to do more work to find these instructions. The other advantage of variable length instructions is flexibility, right? So MIPS, because the instructions have fixed size, 32 bits, every instruction cannot be represented in more than 32 bits. So there's a limit to what a single instruction can encode. Okay, whereas with variable length instructions, we can have very long instructions that do very complex things. Okay, so that gives us more flexibility. So these are the advantages of variable length instructions. But of course, the disadvantage is that if we have variable length instructions, that means we don't have regularity, which means we need more complex hardware. Okay, we need hardware to be able to find where each instruction is, because every instruction is a different size, whereas that is easy to do when every instruction is a fixed size. And we need hardware to decode these very large instructions, which is also complicated. Okay. So this is just kind of a motivation behind the design decisions in MIPS, where every instruction is 32 bits and there's a small number of formats. So now let's see how we can encode the instructions that we've covered so far in 32 bits. I'm going to start by one of the formats. Like I said, there are 3 formats. I'm going to talk about 2 today. The first format I'm going to talk about is the R format. So R format instructions include instructions. Well, I'll show you what they include, but first let me tell you what they look like. So the encoding for the R format instruction is as follows. We have 6 bits. We have the following fields: opt, rs, rt, rd, shift amount, and funct. So the first 6 bits are called op, and these are the operation code. Okay, so these first 6 bits are called the operation code or the op code, and these help encode what instruction we are storing. Okay, what instruction we are representing. The next 5 bits are S, refer to the first source register. Remember, we said that some instructions have 2 source registers and 1 destination register. So here RS and RT are going to be the 2 source registers, and RD is going to be the destination register. So you can obviously tell that the R format instructions are going to be for instructions that have 2 source registers and 1 destination register. Okay, the 2 source registers are RS and RT, and the destination register is RD. Now, one thing you notice is that RS, RT, and RD are all 5 bits. Okay, so we need 5 bits to encode the register number. Where does 5 bits come from? Why do I need 5 bits to represent the register number?
We have 32 registers.
Right, exactly. We have 32 registers. So because we have 32 registers, we need 5 bits. 2 to the power 5 is 32. So 5 bits give us a way to index each of the 32 registers. Okay. Next, we have the shift amount. This is useful for shift instructions. This is also 5 bits. And again, the reason it's 5 bits is because we will only ever shift by 2 to the maximum we will shift by is 2 to the power 5, which is 32, right? It doesn't make sense to shift by more than 32 because the whole word is 32 bits. So if you shift it by 32, that means you've removed the entire value. So there's no point in shifting it more than that. Okay. So the shift amount is how many positions to shift, and this is only used for shift instructions. And then finally, funct is the function code, and this extends the opcode. Okay, the funct field extends the opcode, which means that the opcode and the funct code together for the R format instructions are used to specify what the instruction is. All right. Okay, now I know this is very abstract, so let's do an example. So given I have an R format, one of the instructions that's represented in R format is the add instruction. So add is an R format instruction. When I encode the add instruction in binary, I will use the R format to represent it. So let's see how we can take this instruction, add T0, S1, S2, and encode it using the R format. Okay. Let's start with the opcode. Okay, so the first step is to figure out what is the opcode for add. Okay, to figure out what is the opcode for add. And to do that, we're going to look at something called the MIPS green card. The MIPS green card, or the MIPS reference data sheet, is a sheet that gives you kind of a summary of all you need to know about the core MIPS instruction, the core instruction set of MIPS. So here you have the different instructions and what they are called, and here it also tells you what they do, okay? And if you scroll down a bit, it tells you about the different formats. Right now we're talking about the R format. And if you go to the second page, what it tells you is you have this table called opcodes, base conversions, ASCII symbols. So the first part of this table here gives you the opcode for each instruction. Okay, the opcode for each instruction. What does that mean? So here, in the first column in this table, this is the opcode. It includes these different instructions and their opcodes. So for example, here, add immediate, there's this add immediate instruction. Okay, what this table is saying is that add immediate has the opcode listed over here, which is 00100, which is also equal to 8. So if I have an add immediate instruction, my opcode is going to be 8. So if I want to go, right now what we're doing is we want to figure out what the opcode is for add. Okay, so the way to do that is we're going to look for add in this table, okay, and we're going to find it, and we're going to figure out what its opcode is. So we'll notice that add is down here, okay, add is over here, but what you notice is that add is not in the first column, add is in the second column. And now why is add in the second column? Well, if you go scroll up, you'll notice that the second column refers to MIPS funct. Okay, it refers to MIPS funct. What this is saying is that the add instruction is not represented using the opcode alone. The add instruction is represented using both the opcode and the funct field. Okay, the instructions that are in the first column are represented using the opcode alone, but the instructions that are in the second column are going to be represented using the opcode and the funct field. And how do I know what is the opcode and what is the funct field? In this first column, there's a 1 over here, and this 1 means that the opcode corresponds to where the 1 is over here. Well, the 1 in this opcode column is over here, which means that the opcode is 0 for everything in this column. And then we use the second column to figure out what the funct field is. So here the add instruction has the following funct value, 10000, which is equivalent to 32. Okay, so to summarize, add is in the second column. So add is going to be encoded using both the opcode and the funct field. The funct field is going to be 32 or 10000. And then the opcode for add is going to correspond to wherever the 1 is in the first column, and the 1 in the first column is in 0, so it's going to be 0. Okay, so I know that was kind of a long-winded, but you'll get used to looking at this table and understanding what it means. So for now, I'm just going to say that add is special. Okay, it's a special instruction because it uses both the opcode and the funct field. The next value is going to be RS. So what is RS in this case? What are my two source registers here? I'm doing add T0, S1, S2. What are my two source registers and what are my destination registers? Right, so S1 and S2 are my two source registers. So the first source register, S1, is going to go in the RS field. So here, this is going to be S1. The second source register, S2, will go in the RT field. So this is going to be S2. Okay. My destination register is what? T0. So T0 is going to go in RD. What about the shift amount? Do I do any shifting when I do add? I don't do any shifting when I do add, so I'm just going to put a 0 here. I'm going to ignore it. So this field over here, these 5 bits, they're unnecessary for the add instruction. But I'm gonna reserve space for them anyway because I want my entire instruction to be 32 bits. If I remove them and say, okay, I want to represent my instruction using just 27 bits, sure, that we're going to save space, but it's going to create a lot of lack of regularity. So I'm going to keep these bits here in my instruction, but they're not going to be useful. Okay, and then finally I have the funct field, and like we said, the funct field here is going to correspond to the funct of the add instruction. Okay, so now I have filled out what all these fields are using human readable values. Now let me convert these values to binary. So the special value here for the opcode, we said that for add, it uses the second column, so it's going to use a funct value, and it's going to use the opcode corresponding to 1, and the opcode corresponding to 1 is 0. So here the special opcode for add is going to be 0. What is the value of S1 in terms of numbers? Well, here in the MIPS sheet, we also have the register name, the registers, and here we have the names of the different registers. So here we have each of the 32 registers and their names, okay? And what it also gives us is the numbers for these registers, okay? So like I said before, T0 is register number 8, T1 is register number 9. So T0 to T7 are 8 to 15, S0 to S7 are 16 to 23, and then T8 to T9 are 24 to 25. Okay, and we have a whole bunch of registers which we'll talk about before. We've talked about the 0 register. That's the number for the 0 register is just 0. Okay, and we'll talk about the other registers later. Okay, but for now, for our instruction, we want to know what is the decimal value for, what is the number for S1. Well, S1, if we look at the table, S0 is 16, so S1 is going to be 17. Okay, so we're going to have 17 for S1, and S2, well, S2 is going to be 18. Okay, so we're going to put an 18 for S2. Okay. What about T0? What is the number for T0? Well, let's look at the table. What does the table tell us? Right, the number for T0 is 8, so we're going to put an 8 over here. For the shift amount, 0 is just going to be 0. And for add, we want the funct value for add. Well, let's go back to our table. Okay, the second column tells us the funct. So if we go to the add instruction, which is in the second column, the funct value for add is going to be 32. Okay, so the funct value for add is going to be 32. So now I have the numbers corresponding to each of my fields in the R format of the instruction. Now what I can do is convert it to binary. So what is 0 in binary? Well, I want 0 as a 6-bit binary number. Well, that's just 0, 0, 0, 0, 0, 0. I want 17 as a 5-bit binary number. Well, 17 is 16 plus 1, so it's going to be 1, 0, 0, 0, 1. Okay. I want 18 as a 5-bit binary number. Well, 18 is 16 plus 2, so that's going to be 10010. And then I want 8 as a 5-bit binary number. Well, that's going to be 01000. Then I want 0 as a 5-bit binary number, so that's going to be all zeros. And then finally, I want 32 as a 6-bit binary number, so that will be 100000. Okay, so this sequence of 32 bits, okay, this over here is how we represent add T0, S1, S2 in binary. Okay, so if you have a program and you all you have is the binary for that program, and you see this sequence of bits in this program, and you know this is a MIPS program, then you know that this sequence of bits represents add T0, S1, S2. Okay. And here to the right, I've just represented the instruction in hexadecimal. You guys know how to convert from binary to hexadecimal. You just take every 4 bits and convert them to the corresponding hexadecimal digit. Okay. Any questions about how we converted from this instruction to the R format?
Professor, why up is 0? How did you know that it's 0?
Okay, so the way we knew that up is 0 is we looked up add in this table. Okay, we look for add in this table. If we find it in the first column, then the opcode is just the corresponding number in that column for that column. If we find it in the second column, it means it uses the funct field.
So every time we find in the second column it is 0, the up is
Every
0.
time we find in the second column, it corresponds to the opcode 1, and the opcode for parent 1 in parentheses is 0. Yes. So anything in the second column is going to have an opcode of 0, and the funct field is going to be whatever the number of the column is. So in this case, add has a funct value of 32.
Oh, okay.
Other questions? Okay, well then let me introduce next the MIPS I format. So the I format it looks like this, we have an opcode, we have RS and RT, so these are similar to the R format, but the difference is that rather than having RD, shift amount, and funct, we're just going to have 16 bits, and these 16 bits are going to be used to store a constant or an address. And as you can probably guess, we're going to use the I format to represent immediate and load and store instructions. Okay, that's where the number, that's where I comes from. I comes from immediate. Okay, so this I format is used for immediate arithmetic and load and store instructions. Because we no longer have RD over here, okay, we're actually going to use RT as the destination register. So for IM format instructions, RS is a source register, and RT may either be a source or a destination register depending on the instruction. All right. The constant over here is 16 bits, okay? And with 16 bits, we can only represent 2 to the power 16 numbers. And because we want to be able to represent negative numbers, because like I said before, if we're going to want to subtract a constant, we're going to use add immediate and give it a negative number. So the range that we can, the range of constants that we can represent is going to be negative 2 to the power 15 to 2 to the power 15 minus 1. So that's a total of 2 to the power 16 constants. If we have an address, then these 16 bits are going to correspond to the offset from the base register. So remember how when we had a load instruction, we had a base register and we also had like 32 as the offset? Well, that 32 will be encoded as in this field over here. Okay, having both an R format and I format follows design principle 4, which is that good design demands good compromises. So although we have different formats, and this is a compromise on our principle of being as simple as possible, our formats are going to look similar in the sense that the I format and the R format both have 3 fields in common. And you'll see later on when we design hardware why this is important. Okay? So let me do an example with the I format. So if I have add immediate S1, S2, 100, and I want to encode that, I'm going to encode it using the I format. Okay. What is the I format? Oh, by the way, I forgot to tell you. So the way to know what format each instruction uses is by looking over here. So here the add instruction uses the R format. That's how we know it uses the R format. Add immediate uses the I format. So this table at the beginning tells us what format to use for each instruction. Okay. So the first step is to find the opcode for add immediate. Well, what do? I go to my table over here, and I look through the first column for add immediate. I find it over here. So if this is add immediate in my table, what is the opcode for add immediate? It's going to be 8. Okay, the opcode for add immediate is going to be 8. All right. Because here add immediate is in the first column, which means it only uses an opcode, it doesn't use a funct. And this column is column number 8. Okay, so the opcode for add immediate is going to be 8. What is RS? So here, add immediate has only one source register and one destination register. Okay, the source register, this here means S1 equals S2 plus 100. So S2 is going to be my source register. So S2 is going to go in RS. And S1 is going to be my destination register. So for add immediate, RT will be used as a destination register, and S1 will go in RT. Okay. Now what I have left is the constant. So what am I going to put in the constant field? I'm going to put 100, right, exactly, because 100 is my constant. So in these 16 bits, I will store 100, okay? So now I know what goes in each field, okay? Let me convert them to binary. So we said that the opcode is the opcode for add immediate, and add immediate, the opcode for add immediate is 8. So this add immediate here will be 8. The number for S2, well, I go to the table here. It tells me that S0 is 16, so S2 is going to be 18. So here I'm going to put 18 for S2. S1 will be 17, and then here the constant is just 100. Okay, and then I convert these to binary. So 8 in binary is 00100. 18 in binary is this number over here. You guys know how to convert from decimal to binary. So 17 in binary is this number over here, and 100 in binary as a 16-bit number is this number down here. So this sequence of 32 bits is the add immediate instruction. Okay, we still have the load instruction. The load instruction is going to be very similar. Okay, our opcode is the opcode for load. Okay, our source register in this case, when we load, remember we have a base register, an offset, and then the destination. So this means that we load the value at 100 after S2 and we store it in S1. So the source register is going to be the base register S2. RT, the destination register, will be S1, and the constant will be 100. Okay, and you know by now how to convert these to binary. Load, to find load, we look it up in the table over here. So we find load over here. So the opcode for load is 35. So here we put 35. Okay, and then we saw these before. S2 is 18, S1 is 17, and 100 is just 100. And then we convert these values to binary, and we get the 32 bits that are used to represent the load instruction. And the store instruction is very similar, but the one thing that differs about the store instruction is that a store instruction does not write to any registers. A store instruction reads to registers and writes to memory. So here both S2 and S1 will be source registers for store word. So the opcode is going to be the opcode of store word. The first source register is going to be the base register, which is S2. The RT is going to be S1, the second source register. So here for add immediate and for load, RT was a destination register, but for store, RT is also going to be a source register. And the constant offset is 100, which is 100 over here. And then I want to find the corresponding numbers. So store word, the opcode for store word is going to be, look it up in the table, it's 43. So I'm going to put 43 over here. S2, I look it up in the table up here for registers. So here it tells me S0 is 16, so S2 is 18, S1 is 17, and the constant is 100. Okay, and then I convert these to binary. So 43 in binary is this value, 18 in binary, 17 in binary, 100 in binary as 16 bits. And now I have the 32-bit sequence that represents a store instruction. Okay, so now we know how to represent R format and I format instructions in binary. Next time we will look at more instructions and we will look at a new instruction format for representing control flow instructions. Okay, so if you'd like to read more about what we covered today, you can refer to section 2.5. Are there any final questions before I end? All right, well, if there are no questions, then that is all for today, and I will see you next time. Bye, everyone.